Hi, hi. I am from GANGADHAR Government College, Nizamabad. So, lecturer in mathematics, Department of Mathematics. So, the present topic is BSC third year, subspace and linear span. So, what is a subspace? So, what is a subspace means? So, it is similar to subgroup model. So, subgroup definition we know that H is non-empty subset of group G and satisfies the properties with respect to same composition defined on a group G. Then we say that non-empty subset H is called a subgroup of group G. So here subspace also same definition. So here a subspace V of vector space V is a subset H of V. So let H be non-empty subset of vector space V and satisfies the conditions. 0 is element 0 belongs to H, first one. Second one, U comma V belongs to H, then U plus V also belongs to H. Third one, C belongs to V and U belongs to H, then CU belongs to H. So these three conditions satisfied, then we say that H is subspace of vector space V. Conditions are 0 bar is element of H, so U plus V belongs to H. Next CU belongs to H. So U plus V belongs to H means vector addition satisfied. CU belongs to H means scalar multiplication satisfied. So these three properties satisfied, then we say that it is called a subspace. Or subspace means here we will take H or W. So if W is non-empty subset of vector space V over F, then W is said to be subspace of V. So if the following conditions hold, so 0 vector V in W, U comma V are in V in W, then U plus V is in W. U belongs to V and C is a scalar, then CU is in W. So these three properties satisfied, the non-empty subset of vector space is called subspace of V. So for example 0 vector. So 0 vector satisfies these three properties. So we say that 0 bar, singleton 0 bar is subspace of vector space V and it is also called zero space. So linear combination. So next definition, linear combination. So a vector B in a vector space V is called linear combination of the vectors. So u1, u2, u3, so on uk in V, if B can be written in the form, so B equal to C1 u1 plus C2 u2 plus so on Ck uk, where C1, C2, so on Ck are scalars. Then this expression or this form is called a linear combination of the vectors u1, u2, so on uk. So B value we write C1 u1 plus C2 u2 plus Ck so on plus Ck uk. Then we say that B is linear combination of the vectors u1, u2, so on uk. So here C1, C2, so on Ck scalar values are exist. C1, C2, so on Ck scalar values are exist. Then we say that B is linear combination of the vectors u1, u2, so on uk. So now one example. So three vectors are given v1, v2, v3. So now we check another vector is given w. So now we verify w is linear combination of the vectors v1, v2, v3 okay or not. So first we write w is linear combination of the given vectors c1 v1 plus c2 v2 plus so on c3 v3. W equal to we write 1 1 1 equal to c1 into v1 value 1 2 3 plus c2 into 0 1 2 plus c3 into minus 1 0 1. So we get right side equations. First ordinates c1 minus c3, second ordinates 2c1 plus c2 comma third ordinates 3c1 plus 2c2 plus c3. So we compare both side coefficients, then we get three equations. So those three equations are c1 minus c3 equal to 1, 2c1 plus c2 equal to 1, 3c1 plus 2c2 plus c3 equal to 1. So these three equations are solved for c1, c2, c3. So if c1, c2, c3 values are exist, then we say that W is linear combination of the vectors v1, v2, so on v3. If the scalars c1, c2, c3 values does not exist, then we say that W is not linear combination of the vectors v1, v2, v3. So here, these three equations we solved for c1, c2, c3 values. So last value we will take, suppose c3 value we say that t, then we get c2 equal to -1 minus 2t, c1 equal to 1 plus t. So here we will take t is a parameter. So t is a parameter means, it contains infinite values. Constant means it has only one value. It has only one value is called constant. It have infinite values is called a parameter. So here t is a parameter, we get c1, c2 values in t. So for different values of t, we get different values for c1, c2, c3. So this system, here the system is say infinite many solutions. If this system has infinitely many solutions, suppose I value, t value 1, then W equal to, we write 2v1 minus 3v2 plus v3. So we say that suppose c value 1, there is c3, suppose t value 1, then we get c1, c2, c3 values like 2 minus 3, 1. So we say that W is linear combination of the vectors. So W v1, v2, v3. So next definition is the linear span. So linear span means a set of possible linear combinations defined on a given set is called a linear span of the set. So the set of all the vectors that are the linear combinations of the vectors in the set S equal to v1, v2, so on vn is called span of S, and it is denoted by span of v1, v2, so on vn, or span of S, or linear span of S. Suppose the set elements are S equal to v1, v2, so on vn, then L of S definition is a1 v1 plus a2 v2 plus so on plus an vn, such that v1, v2, so on vn belongs to V, and a1, a2, so on an belongs to F. So set of all linear combinations defined on set of all linear combinations defined on the set S is called linear span of S. So v1, v2, so on vp are in vector space, then span elements are, we write span of v1, v2, so on vp. So this set is a subspace of V. Subspace of V means that set satisfies three properties of subspace. So 0 bar belongs to span of S, and U plus V belongs to span of S, and Cu belongs to span of S. So then we see that span of S set is a subspace of vector space V. So here we will take one example. So given v1, v2 in a vector space V, let H is a span set of v1 comma v2, show that H is a subspace of V. So first subspace means we show that 0 bar is element of H, next to U plus V belongs to H, next to Cu belongs to H. So these three properties satisfied, then we say that H is subspace of V. So first the 0 vector in H, 0 equal to, we write span set means we write a linear combination of the elements. Linear combination of the elements is called span set. So we write 0 bar equal to 0 v1 plus 0 v2. So we say that 0 bar is element of H. Next we will take two elements from U comma W, two elements from H. So H means these two elements are span of v1 comma v2. So U value we will take S1 v1 plus S2 v2, and W value we will take L1 v1 plus L2 v2. So first, what is the first axiom? U plus W. So U plus W value we get S1 plus L1 into v1 plus S2 plus L2 into v2. So here it is a linear combination of v1 v2. So we say that U plus W is element of H. so u plus w in H. So that first second property is satisfied. For third property, we will take C is any scalar and u value S1 V1 plus S2 V2. So now we find Cu value. Cu value we get CS1 into V1 plus CS2 into V2. Means here it is the span of V1 V2. So we say that Cu belongs to H. So here H elements span of V1 V2 satisfies 0 belongs to H and u plus v belongs to H, Cu belongs to H. So therefore we say that H is subspace of vector space V. So this way we find subspace. So next problem, let H be the set of all vectors of the form. So elements of H are the form A minus 3b, comma b minus a, comma b. So where a comma b are arbitrary scalars. That is, H value is elements of H. Elements of H are in the form a minus 3b, comma b minus a, comma b, such that a comma b belongs to R. So here we show that H is subspace of R4. So H is subspace of R4 means elements of H are we write a linear combination of the vectors. Then we say that H is subspace by previous theorem. So here elements of H value we write in column model. In column model we write a minus 3b first element, b minus a second element, a third element, b fourth element. So a common, a values we write first. A values, a coefficients are 1, minus 1, 1. So last row a is not there, so we will take 0. Plus b into b coefficients are in the first row minus 3, second row 1, third row b is not there, so 0, fourth row b coefficient is 1. So a into vector, b into vector. So we say that it is a v1 plus b v2. So we write H is span of v1 comma v2. H is span of v1 comma v2. So H is linear combination of the elements of H are linear combination of the vectors v1 comma v2. So we say that previous theorem H is subspace of vector space. So here 4 ordinates are there. So we say that it is subspace of R power 4 or R4. So next problem. Show that the set H of all points in R2 of the form. So elements of H are in which form? 3s comma 2 plus 5s. So show that it is not a vector space. So by showing that it is not closed under scalar multiplication. So here we show that scalar multiplication is not satisfied. So here first we will take any u in H, say u value 3 comma 7 example, and c value we will take 1. C is not equal to 1. Then Cu, what is Cu definition? C into u definition. So 2 into C value, C not equal to 1 and say C value 2. Suppose we will take C value 2, then Cu 6 to 14. So if this is Cu is in H, then there is some S such that 3s plus 2 plus 3s. Here we apply definition 3s plus 2 plus 5s equal to 6 to 14. So first elements of H are which form? 3s comma 2 plus 5s form. So we will take one value for C2 and u value we will take 3 comma 7. We get 6 comma 14. So it is also element of H. So u plus v belongs to H means, so we equate these two values 3s 2 plus 5s 6 14. So we get 3s equal to 6 and 2 plus 5s equal to 14. From the first definition we get s equal to 2, second definition s equal to 2 by 15. So which is not possible. In the both cases we get s value is equal. So here one case we get 2, another case we get 12 by 5. Means these two values are not equal. So we say that s value does not exist. Means, so here first property not satisfied. U plus v does not belongs to H. So we say that therefore H is not a vector space. So now second problem. So let W be the union of the first and third coordinates in the xy plane. So W value we will take x comma y such that xy greater than or equal to 0. So we verify next one problem for W, another problem for V. Elements of V are the form xy ordinate order pair of x comma y or column x comma y such that x greater than or equal 0 comma y greater than or equal 0. So xy satisfies these two conditions, then we say that xy is element of V here. So then what is the problem? So if u is in W and c is any scalar, then cu is in V, cu is in W, so y. So u belongs to W, c is scalar, then we check cu is element of W or not. Second question is find the specific vectors u and v in W such that u plus v is not in V. So here we find two vectors u comma v. So u comma v, here we find two vectors u comma v such that u plus v does not belongs to W. So now first condition for W. So we will take two vectors. So we verify that property is satisfied or not. So if u and v are in V, then their entries are non-negative. Since the sum of non-negative numbers is non-negative, the vector u plus v as non-negative, then u plus v in V. So it is the answer of second one. Or equals 0 means positive number, y greater than or equals 0 means positive number. So in the sum u plus v, we get x plus y. So sum of two positive numbers is positive number. So we say that in the V, so u plus v condition satisfied. So in the V we verify second condition satisfied or not. U value we will take 2 comma 2 and c value negative. Then cu is we get negative. So positive into negative value we get negative. So cu does not belongs to F. For second, in the V definition, second property does not exist. So product of positive and negative value we get negative, not positive. So in the V second problem, first condition u plus v belongs to V and second condition not satisfied. So now we check W problem, first problem. So here xy greater than or equal to 0. Xy greater than or equal to 0 means u is x comma y in W and we will take c value is c. So now we verify cx into cy. Cx into cy equal to c square into xy greater than or equal 0. So that property is satisfied or not. C is either positive or negative. X comma y both are positive. Then product of two positive numbers is c square means it is a positive. Xy also greater than or equal 0. Positive into positive means positive. So that property is satisfied. So in the second, u plus v does not belongs to in W. So because u value minus 1 minus 7 and v value 2 3, then what is u plus v value? Minus 1 minus 1 minus u plus v value minus 1 minus 4. So their product value minus 1 into minus 4, minus 1 into minus 4, minus 1 into minus 4 value we get 4. So then so here one is 7, first one is positive, second one u plus v, their product value u plus v minus 1 example is not okay here. So we will take plus 1. So plus 1 plus 1 plus 1 plus 2 plus 3 into minus 4. So minus 12, that value less than 0 means property not satisfied. X into y not greater than 0. So we say that this way we will define the properties here. So now the third problem. So let H be the set of points inside and on the unit circle in the xy plane. So that is h equal to xy such that x square plus y square less than or equal to 1. So then find specific example. Two vectors are s vector or a scalar to show that h is not subspace of R2. Means elements of h not satisfies that property. So we will take u value 0.5, 0.5 and c value 4. So c into u we find. C into u value, what is c into u value? 0.5. 0.5 means 4, 0.5. C into u, 0.5 into 4, 2. So we get 2 square plus 2 square. 2 square plus 2 square means, so 4. So 4 not less than or equal to 1. 4 not less than or equal to 1. So in the h elements, x comma y ordinate satisfies x square plus y square less than or equal to 1. Then we say that x comma y belongs to h. So here 0.5, 0.5, c value 4. Then we get result value 4 not less than or equal to 1. So we say that, so that property not satisfied. So we say that h is not subspace. So next problem. So let h comma k be two subspaces of vector space V. Then show that here h intersection k, not hk. H intersection k is subspace of V. H intersection k is subspace of V. So we verify h intersection k satisfies the subspace conditions or not. So first h comma k are two subspaces of vector space V. So h comma k are two subspaces means these two sets satisfies three conditions of subspace. So those are 0 bar belongs to h comma k, u plus v belongs to h comma k, cu belongs to h comma k. So by using these three properties we applied for h intersection k also. So now first 0 belongs to h, 0 bar belongs to h, 0 bar belongs to k. The intersection definition is set of all common elements between two sets. So here both h and k contain 0 vector of V because they are subspaces of V. So thus 0 is vector of V is in h intersection k also, means first condition satisfied. For second condition, let u and v be u comma v belongs to h intersection k. Then u comma v are in h and k also. U comma v are in h, then u plus v belongs to h. So u comma v belongs to k, then u plus v belongs to k. So u plus v is element of h and k also. So we say that u plus v is element of h intersection k. So means second condition satisfied. So for third condition, so u is element of h and k, c is any scalar. Then cu comma ck are elements of h and k. So these two values are common elements. Cu belongs to h and cu belongs to k. Cu is common element of h and k. So we say that cu is element of h intersection k. So h intersection k satisfies three properties. So 0 vector belongs to h intersection k, u plus v belongs to h intersection k, cu belongs to h intersection k. So if these three properties satisfied, then we say that that set is a subspace of vector space. So therefore we say that h intersection k is a subspace of V. So here one note is there. So that note is, so union of two subspaces need not be subspace. Union of two subspaces need not be subspace. So for example, so we will take two sets h equal to elements are x comma 0 and k equal to elements are 0 comma y. X comma 0 means it is ordinates of x axis, 0 comma y means ordinates of y axis. So elements of h are x comma 0 form, elements of K are 0 comma y form. So then what is H union K? H union K means elements of H union K are either x axis elements or y axis elements, means either x comma 0 form or 0 comma y form. H union K elements are the form x comma 0 or 0 comma y form, but u value x comma 0, v value 0 comma k, then we get u plus v equal to x comma y. So it is not element of H union K. So we say that union of two subspaces need not be subspace. So here some problems are there. So given determine if the given set is a subspace of n for an appreciate of values of n, justify your answers. So all the polynomials of the form p of t equal to at square form, So here the elements of h are a into t square form. So it is second degree polynomial set. So now we verify. So this set satisfies subspace properties or not. Subspace properties are 0 bar belongs to H, u plus v belongs to H, cu belongs to H. So these three properties satisfied, then that set form a subspace of vector space V. So now elements are the form at square. At square means 0 vector we write 0 into t square. At square equal to 0 bar means that value we write 0 into t square. So 0 into t square means that property satisfied. Next at square plus bt square. A plus b into t square means second property also satisfied. So c into at square, ca into t square. So here given set elements are the form second degree polynomial form. 0 into t square value 0 bar means first condition satisfied. A plus b into t square means this one also second degree polynomial, second condition satisfied. C into at square, ca into t square means third condition also satisfied. So we say that fifth problem satisfies total three conditions of subspace. So we say that it is a subspace of V. Or so we know one theorem. So elements of the subset, elements of the non-empty set, we express linear combinations or span, then we say that span set is a subspace. Direct we say that. So here p of t equal to at square means a into t square. So t square is linear combination. So we say that direct it is subspace. So next second problem, p of t equal to a plus t square. So here 0 vector. So what is the 0 vector? A plus t square equal to 0. Then that value we write right side 0 into t square. So a, what is a value? Here we can't get a value. So we say that for 0 does not exist. 0 does not exist. Same way we say that a into 1 plus 1 into t square. So 0 value does not exist. So here in the sixth, so 0 value does not exist. So we say that it is not a vector space. So in the seventh problem, all the polynomials of degree at most 3 with integer as coefficients. So degree at most 3 means degree of the polynomial is less than or equal to 3. So degree of the polynomial is less than or equal to 3. Here the coefficients are integer coefficients. Coefficients are integer coefficients. So in all problems, coefficients are real numbers. So here in the Pn, so polynomial coefficients are real numbers. So okay, so here in the seventh problem, polynomial coefficients are integers. So field set is real number set. Coefficients are real numbers, integers means. So third property, what is third property? C into U. C is real number, U is integer. So we know that integer into real number is real number, not integer. Means that property not satisfied. Third property not satisfied. Integer into real number is integer, not integer into real number is real number. So we say that property not satisfied. So next, all polynomials in Pn such that p of 0 equal to 0. So p of 0 equal to 0 means first property satisfied. Second, p plus q of 0 equal to p of 0 plus q of 0, that equals 0 plus 0 equal to 0. Next, c into p of 0 equal to cp of 0, that equal to 0. Means three properties satisfied. So we say that this set also a subspace. So here the next problem. So let H be the set of all vectors of the form minus 2t, 5t, 3t. Find a vector in V R3 such that H equal to span V. So why does this show that H is subspace of R3 or not? So elements of H we write linear combination means span of V, then we say that H is subspace. So here T common, T into either column or row, H equal to T into minus 2, 5, 3 such that T belongs to R. Then H value we write span of minus 2, 5, 3. So here H equal to span V is subspace. So therefore we say that H is subspace of R3. So here next one problem. So let H comma K be two subspaces of vector space V. Then show that H plus K is also subspace of V. H plus K is also subspace of V. In the previous we know H intersection is subspace. So but union H union K is not subspace. So here H plus K is subspace of V. So we will take H comma K be two subspaces of vector space V. We define H plus K set. So H plus K set elements are H plus K such that H belongs to H comma K belongs to K. So first H comma K are two subspaces means these two are satisfies three conditions of subspace, that is 0 vector is element of H comma K, U plus V belongs to H comma K, Cu belongs to H comma K. So UV so here H plus 0 bar plus 0 bar equals 0 bar belongs to H plus K. Next we define two vectors W1 comma W2. So these two are the form U1 plus V1, U2 plus V2. U elements are belongs to H, V elements are belongs to K. U elements are belongs to H, V elements are belongs to K, W elements are belongs to H plus K. So now we write W1 plus W2, W1 plus W2 equal to U1 plus U2 plus V1 plus V2. U elements belongs to H and V elements belongs to K. So what is W1 plus W2 belongs to H plus K? Means satisfies first property. Second one, CW1. CW1 equal to C into U1 plus V1. CU1 plus CV1. CU1 means it is belongs to H plus CV1 means belongs to K. So CW1 belongs to H plus K. So third property also satisfied. So here three properties are satisfied. So we say that H plus K is subspace of V. So next problem. So let W be the set of all vectors of the form 2B plus 3C minus B 2C. So where B and C are arbitrary, find vectors U and V such that W equal to span of U comma V. So here we verify. So elements of W are we write span of U comma V or not. So if W is span of U comma V, then we say that W is subspace of R3. So what is the H value? H value is H or W. So H equal to column we write. So how many constants are there? b comma c, two constants are there. So first we write b coefficients. So in the first row b coefficient 2, second row b coefficient -1, third row b is not there, so we write 0, 2 minus 1 0. Next plus c into, so first row c coefficient 3, so second row c is not there, so we write 0. So third row c, what is c coefficient 2, so b into 2 minus 1 0, 2 minus 1 0, plus c into 3 0 2. So we say that is equal to span of 2 minus 1 0 comma 3 0 3 0 2. So we say that span uv. So u comma v two vectors are exist. So we say that H is span of subspace of R3. H is subspace of R3. Same way, next problem, let W equal to set of all vectors of the form 2s plus 4t, 2s, 2s minus 3t, 5t. So here s into, we write s into 2 comma 2 comma 2 comma 2 comma 2 comma 0 plus t into 4 comma 0 comma minus 3 comma 5. So here also elements of W are span of u s into some vector v1, we say that t into some vector v2. So v1 v2, so we say that it is subspace of 4 ordinates are there, so we say that subspace of r to the power 4. Next problem is, so let v1 equal to 1 0 minus 1, v2 equal to 2 1 3, v3 equal to 4 2 6, and w equal to 3 1 2. So what is the first problem? Is w in v1 v2 v3. So w is element of v1 v2 v3 or not. So how many vectors are in v1 v2 v3? How many vectors are in span of v1 v2 v3? So is w in the subspace spanned by v1 v2 v3? Why? So now first we verify w is span of v1 v2 v3 or not. So now first v1 v2 v3, so we check the v2 and v3. What is the relation there we get? So v2 equal to 2 1 3, v3 equal to 4 2 6. So v3 value we write 2 into, in v3 2 common, then we get 2 1 3. So v3 value we write 2 into v2, means v3 is linear combination of v2. v3 is linear combination of v2, means in the given set one vector is scalar multiplication of another. So we say that the vector w is not in the set. So w is not in the set means w is not a linear combination of the vectors v1 v2 v3. Since w equal to 2 into, not w, that one v2 equal to 2 into v3. So and there are 3 vectors in the set v1 v2 v3. So next second, so the set span v1 v2 v3 contains infinitely many vectors. So that way we write, so here v3, so v3 equal to 2 into v2 means that way we define so many vectors in the set span of v1 v2 v3. So last w is spanned by the vectors or not. So we write w equal to x1 v1 plus x2 v2 plus x3 v3, and we find x1 x2 x3 values. So we write the equations, and those equations are solved for x1 x2 x3. Then we get x1 1, x2 1, and x3 value 0. So we say that w is linear combination of v1 v2 v3. So here method to check span of v. So how we say that vector is element of span of v? First choose an arbitrary vector b in v. So first we will take one vector in v, and that express b So choose one vector b in V. So that b value we write a linear combination of the vectors b equal to k1v1 plus k2v2 plus so on plus knvn. So if the system, so there we say that that system is called a non-homogeneous system or linear system. So if the system of the equations in the above is consistent for all the choice of B, then vectors v1, v2, so on vn span V. So if it is inconsistent for some choice of B, vectors do not span off B. So if the system, so we know in the matrices Ax equal to B. Ax equal to B means it is a linear system. So that system is consistent, then the given equations have solution. If the system is inconsistent, then the given system has no solution. So how we say that consistence or inconsistence means in Ax equal to B linear system, augmented matrix we define. Box AB matrix is called a augmented matrix. So that matrix is reduced to echelon form, means upper triangular form, by using matrix row operations. So first given equations we write in matrix form Ax equal to B form. In that box AB matrix we write box AB matrix is reduced to echelon form. Echelon form means upper triangular form. So by using matrix row operations only, then we find the rank. What is the rank? So then rank of box AB and rank of A are equal, then the linear system is consistent and it has solution. So what is the rank? Rank of in echelon form, rank of matrix is total number of non-zero rows. So in echelon form, rank of matrix is total number of non-zero rows, or rank is the number of non-zero rows in the row reduced form of the matrix is called rank of the matrix. So rank of the matrix is total number of non-zero rows in the row reduced form, means that form we make upper triangular form. So upper triangular form means we make below diagonal elements are zeros. So if in the square matrix below diagonal elements are zeros, then that matrix is called upper triangular matrix. So the rank of m by n matrix non-negative integers cannot be greater than either m or n. So that is rank of A is less than or equal to minimum of order of matrix m by n. So here one example is given. So show that the set S equal to 1 2 3 0 1 2 minus 2 0 1 span of R3 or not, we verify. So first we write a linear we will take one vector from R3. That vector we write a linear combination C1 V1 plus C2 V2 plus C3 V3. Then we get equations C1 minus 2 C3 equal to U1, 2 C1 plus C2 equal to U2, 3 C1 plus 2 C2 plus C3 equal to U3. So compare both side values, or that value we write Ax equal to B form. So there we write coefficient matrix A. So det A not equal 0. So det A not equal 0 means if the system has only one solution. So if the system has only one solution means C1, C2, C3 values are exist. So we say that S is span of R3. So next one problem is there, for what values of H will Y be in the subspace of R3 spanned by V1, V2, V3 if. So here we write Y equal to C1 V1 plus C2 V2 plus C3 V3, and those equations are solved for C1, C2, C3, then we get the H value is 5. So now the end. Thank you.